Now we shall study about wave optics in ray optics and optical Now we shall study about wave optics or physical properties of optics. In 1637, Descartes gave the corpuscular model of light and derived Snell's law. It explained the laws of reflection and diffraction of light at an interface. The corpuscular model predicted that if the ray of light or refraction bends towards the normal, then the speed of light would be greater in the second medium. This corpuscular model of light would be greater in the second medium. The corpuscular model of light was further developed by Isaac Newton in his famous book entitled Optics. And because of the tremendous popularity of the book, the corpuscular model is very attributed to Newton. In 1678, the Dutch physicist Christian Huygens put forward the wave theory of light. It is this wave model of light that we shall study in this article. The wave model could satisfactorily explain the phenomenon of reflection and diffraction. However, it predicted that on refraction, if the wave bends towards the normal, then the speed of light would be less in the second medium. This is in contradiction to the prediction made by using the corpuscular model of light. It was much later confirmed by experiments, when it was shown that the speed of light in water is less than the speed of air, confirming the prediction of the wave model. Foucault carried out this experiment in 1850. Light could travel through vacuum, and it was felt that a wave would require a medium to propagate from one point to other. However, when Thomas Young performed his famous interference experiment in 1801, it was formally established that light is indeed a wave phenomenon. The wavelength of visible light was measured and found to be extremely small. Light can be assumed to be approximately travel in straight lines. This is the field of geometric optics. It neglects the finiteness of the wavelength. After so many years, many experiments were carried out involving the interference and diffraction of light waves. It is explained by assuming a wave model of light. Thus, about the middle of 19th century, the wave theory seemed to be very well established. The only difficulty was that a wave required a medium for its propagation. How could light waves propagate through vacuum? This was explained when Maxwell put forward his famous electromagnetic theory of light. Maxwell had developed a set of equations describing the laws of electricity and magnetism, and using these equations, he derived what is known as the wave equation, from which he predicted the existence of electromagnetic waves. Thus, according to Maxwell, light waves are associated with the changing electric and magnetic field. Changing electric field produce associated with the changing electric and magnetic field. Changing electric field produce a time and space varying magnetic field, and a changing magnetic field produces a time and space varying electric field. The changing electric and magnetic fields result in the propagation of electromagnetic waves even in vacuum. As in principle, when we drop a small stone on a calm pool of water, waves are spread out from the point of impact. Every point on the surface starts oscillating with time. At any instant, a photograph of surface would show circular rings on which the disturbance is maximum. Clearly, all the points on such a circle are oscillating in phase because they are at the same distance from the source, as shown in the figure 1. Such a locus of point which oscillates in phase is called a wavefront. Thus, a wavefront is defined as a surface of constant phase. The speed with which the wavefront moves outward from the source is called the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront. If we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude and vibrate in the same phase are spheres. And we have what is known as spherical waves as shown in figure 1a. At a large distance from the source, a small portion of the sphere can be considered as plane, and we have what is known as a plane wave in figure 1b. Huygens principle allows us to determine the shape of a wavefront at a later time tau. Thus, Huygens principle is essentially a geometrical construction which gives the shape of the wavefront at any time, allows us to determine the shape of the wavefront at a later time. Now, according to Huygens principle, each point of the wavefront is the source of the secondary disturbance, and the wavelets emanating from these points are spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a later time. Thus, if we wish to determine the shape of the wavefront at t = tau, we draw a sphere of radius b tau from each point on the spherical wavefront, where we represent the speed of the waves in the medium. The new wavefront shown as G1, G2 in figure 2 is again spherical with point as the center. We can use Huygens principle to determine the shape of the wavefront for a plane wave propagating through a medium in figure 3. Now, refraction and reflection of plane wave using Huygens principles. As shown in figure 1a. Plane wave is incident at an angle I on the surface PP dash separating medium 1 and medium 2. The plane wave undergoes refraction and C represents the refracted wave front. The figure corresponds to V2 smaller than V1, so that the refracted waves bends towards the normal. Refraction of a plane wave. We shall now use Huygens principle to derive the laws of refraction. Let PP dash represent the surface separating medium 1 and medium 2 as shown in figure 1. Let V1 and V2 represent the speed of light in medium 1 and medium 2. We assume a plane wave front I propagating in the direction A dash incident on the interface at an angle I. Let tau be the time taken by the wavefront to travel the distance BC. Thus BC = V1 tau. In order to determine the shape of the refracted wavefront, we draw a sphere of radius V2 tau from the point A in the second medium. Let C represent a tangent plane drawn from the point C onto the sphere. Then A = V2 tau and C would represent the refracted wavefront. If we consider the triangles ABC and AEC, we readily obtain sin I = BC but AC = V1 tau by AC, and sin R = A by AC = V2 tau by AC, where I and R are the angles of incidence and refraction. Thus, sin I = sin R = V1 by V2. If R is smaller than I, it means if the ray bends towards the normal, the speed of the light wave in the second medium V2 will be less than the speed of light wave in the first medium V1. This prediction is opposite to the prediction from the corpuscular model of light. Now if C represents the speed of light in vacuum, then N1 barabar C by V1 and N2 barabar C by V2 are known as therefore active are known as the refractive indices of medium 1 and medium 2. N1 sin I1 barabar N2 sin IR by Snell's law of refraction and lambda 1 by lambda 2 barabar BC by AE barabar V1 by V2 or V1 by lambda 1 barabar V2 by lambda 2. The frequency nu remains constant even if the wavelength and speed of the propagation decrease for dense medium or V2 smaller than V1.